Okay, so this is the outline of chapter 30. So first of all, we will introduce Faraday's law and Lenz law. And then we'll talk about the induction and energy transfer, and then the induced electric field. Okay, so all of them are about the Faraday's law. All of them are about Faraday's law. Okay, and then we'll talk about the inductor, which is the inductor and inductance, which is actually the third circuit element we learned. We already learned capacitor in chapter 25, resistor in chapter 26, and then here we learn about inductor. Okay, so for the usually using the symbol will be like the capacitor using C, the resistor using R, and then the inductor using L. So usually we will call it RLC circuit. These are the three fundamental circuit elements for the electric circuits. Okay, so and actually in chapter 27 and chapter 31, we will learn a bit about the circuit theory. Okay, and then we talk about the self-induction, RL circuits, energy stored in the magnetic field, and then energy density in the magnetic field. Finally, we talk about mutual inductance, mutual induction, which is actually the transformer. Okay, the transformer, 变压器. Okay, so here we talk about the Faraday's law and Lenz law. So here is some introduction about these two laws. So first, we look at an experiment set up. Okay, so it says a conducting loop is connected to a sensitive ammeter. Ammeter means a device to measure the current, to measure a current of a loop. Okay, so here you can see this is the ammeter. This is the ammeter. In Chinese, it's called 电流计. Okay, 电流计. Okay, so here there is a word sensitive. Sensitive means this ammeter can measure small current, and then it says sensitive ammeter. Okay, so a conducting loop. So we only have a loop here. We don't have any battery connecting to this loop. So if you don't put anything nearby, there won't be any current. Okay, we just put a ammeter and then in series with this loop. Okay, so without this, there shouldn't be any current. Okay, so if you just remove this hand and the magnet bar, then this ammeter will show zero current here. Okay, so because there is no battery or other source of EMF induced, there is no current in the circuit. Okay, so however, if we move a bar magnet towards the loop, a current suddenly appears in the circuit. Okay, so if you put this close to it, and then a current suddenly appears in the circuit, and then the current disappears when the magnet stops moving. Okay, it doesn't really matter whether it is close enough. It related to the movement of the magnet bar. Okay, if it originally this magnet bar is far away, and then you try to push it close to the loop, and then there will be current. And then even this bar is close, but if it stops, then there will be no current. Okay, it depends on the movement itself rather than the occurrence of the or the existence of the magnet bar. Okay, so yeah, so when the magnet stop moving, the current disappear. Okay, if we then move the magnet away, a current suddenly appears, but now in the opposite direction. Okay, so if you move it away, there is still a current, but in opposite direction. So this is the first experiment, and then you can regard these are the observation of this experiment. Okay, so we do not talk about the numbers yet, but we only see the phenomenon here. Okay, so so here it says if we experiment for a while, we would discover the following. Okay, so he summarized. Okay, some points to which worth noticing. Okay, so it says a current appears only if there is a relative motion. Relative motion. It means that if this is just put it there, it doesn't move, and then you move the magnet bar close to it, there will be current. Or the other way around, if this magnet bar don't move, you try to move this whole thing close to the magnet bar, there will still be a current. So it is a relative motion between the magnet bar and this loop. Okay, relative motion between the loop and the magnet bar. Okay, one must move relative to the other. If they are moving together, then there won't be any current. Okay, so the current disappears when the relative motion between them cease. Okay, so depend on the relative motion. Of course, finally, the Faraday's law does not tell you, oh, it is about the movement, but yeah, later on it will tell you, oh, it is actually related to the B field across this cross-section area. Okay, but yeah, this is the later story. So here we just do this simple experiment to observe some interesting facts. Okay, so here it says faster motion of the magnet produce a greater current. Okay, faster. If you move faster, the current will be greater. Okay, if the movement if moving the magnet bar north pole towards the loop causes say clockwise current, then moving the north pole away cause counterclockwise current. Okay, so it relates to the direction of the current, to the direction of the movement. Okay, if you move north pole to it, and then there will be a current in one way, and then if you move the north pole away, and then the current will goes to another direction. Okay, and then if you move south pole, okay, so north pole and south pole towards, okay, north pole towards, south pole towards or away, also cause current, but in reverse direction from the north pole effect. Okay, so it also related to which pole you are using. Okay, yeah. So yeah, okay, which means that it relates to the direction of the B field. Okay, it relates to, but the later story. So there's just some observation, still some observation. Okay, so here is the next setup. So just now we need a magnet bar, and then we move towards and move away. Here we try to change the magnet bar and movement to this circuit. Okay, we don't really move them at all. Okay, we just try to switch it on and off. Okay, so let's see. For this part, it is the same as the previous setting, and then for this one, we have another loop. Okay, playing close to this loop. Okay, and then you see for this loop, it connects to a this is a resistor, and then this is a switch, and then this is a battery. Okay, so if it is open, there won't be any current, and then if you close the switch, there will be current, and then the direction should be like this, because this is positive. Okay, you can see this is positive, this is negative. Okay, so the current should be in this direction, like this. Okay, so in previous chapter we already know that if there is a current going through this loop, it will generate a B field. Okay, what is the direction? Does it it should be perpendicular to this plane. Okay, is this a B field pointing to this side or that side? If you switch it on, bottom left or top right? Okay, top right, using the right hand rule. Okay, you use your finger, follow the direction of the current, and then your thumb will point to the top right direction. Okay, so it will generate a B field pointing the B field will be pointing to that side. Okay, or maybe I just use red color. Okay, this is the direction of the B field. Okay. Okay, so which means that we can, if you just let the switch open, there won't be any current, and then there is no B field generate. If we just close the switch, there will be current, and then generate a B field pointing to the top right direction. Okay, so here it says, for this experiment, we use the apparatus, which means a device with the two conducting loops close to each other, but not touching. If we close the switch to turn on a current in the in the right hand loop, the meter suddenly and briefly register a current. Okay, there will be a current. If you just switch it on, switch this loop on. Okay, there will be suddenly a current, and then this current will disappear soon. Okay, it just appear for a short moment. Okay. And then if the switch remain closed, no further current is observed. So it is like if I just try to, for example, this is the current. Okay, I just try to write it like this. Okay, this is the time. This is the time. And then if originally there is no current, and then if I just switch it on at this moment, there will be a current going up and then disappear. Maybe not necessarily triangle, maybe something like this. Okay, there will be a current appear for a short moment, and then okay, it drop down. Okay, this moment you try to switch on the circuit, switch on S. Okay, and then the current will go to 0, and then yeah, so if the switch then if we then open the switch, so here it means that this is open, this is on stage, but when you try to switch it off, okay, the red line means whether it is on and off. This is off, this is off. Okay, when you turn it off at this moment, okay, you make this switch open, then there will be no current and then no B field, but there will be another sudden and brief induced current appear in the left hand loop, but in the opposite direction, which means that the current will be something like this. Okay, this one and this one are just opposite to each other. Okay, and then it will go back to 0 soon. Okay, so we get an induced current from an induced EMF only when the current in the right hand loop is changing. Okay, so this changing is very important. Okay, it's related to the Faraday's law, and either turning on or turning off, and not when it is constant. Okay, even if it is large. Okay, okay. So finally he said, oh, what is this something? Apparently, cause when something changes. But actually, I just tell you already, which is actually the magnetic flux of this loop. Okay, so what is this something? Oh, Faraday's no. Okay, but I also know. Okay, so here, yeah, it says that Faraday realized that an EMF and a current can be induced in a loop, as in our two experiment, by changing the amount of magnetic field passing through the loop. Okay, actually for both of the experiment, we are trying to change the magnetic flux of this loop. Even for this one, for this one, you can see if this is far away, which means that originally the bar is far away, and then the B field will be something like this. So which means that the B field magnetic flux going through this loop is smaller, and then if you place it closer and closer, you can see this part is stronger. If you place even closer, the B field will be even stronger, which means that the magnetic flux become larger and larger. when you're placing when you're moving the magnetic bar close to the loop. And if you're moving it away, okay, and then the magnetic flux is still changing, but the magnetic flux of the loop becomes smaller and smaller, but it's changing, okay. So that's the idea here. Oh, sorry. Okay, so for here, originally, if this circuit is open, then there won't be any B field. And then if you suddenly turn it on, it becomes current I and then generate a B field, okay? And of course you can calculate the value, but yeah, the value itself is not very important. It's just a number, okay? So it just turn from 0 to a positive number. So there will be a magnetic flux change when you just switch it on. Okay, so there will be a current, and then after this is on for a moment, then the magnetic flux across this loop doesn't change at all, so there won't be any current. And then if you just switch it off, then there will be a change for the magnetic flux here, change from a positive value back to 0. So there will be a changing. Okay, so so there will be a current, okay, in the other direction. Okay, so it related to how the magnetic flux change. Okay, so here it says the magnetic flux phi b through an area in a magnetic field B is defined as this one. Okay, so it is yeah, actually we have already learned the electric flux in chapter 23 when we learned the Gauss law. So at that time, okay, so this is electric flux. Okay, electric flux. Okay, if we don't have a circle, it is the total flux. I mean the total flux. Okay, the total flux. And then if we have a circle here, okay, it becomes a net flux for a closed surface. But here we don't necessarily for a closed surface. This is just a circle. It is not a closed surface. Okay, so here we only have the integral sign without a circle. So yeah, so here it says the SI unit for this magnetic flux is Weber. Okay, it's Weber. This is the SI unit, so you need to remember it. Okay, actually the Weber is like, this is Tesla. Okay, so we have Tesla times area. Area is meter square. Tesla times meter square is Weber. Okay, so we use this as the SI unit for the magnetic flux. Okay, so if B and A are perpendicular to each, are parallel, I mean parallel because they are in dot product, and then if B field are also uniform, then this surface integral will be simplified to a multiplication. Okay, so you just multiply the B field by the cross-section area. Okay, so in high school physics, maybe you have seen this formula before, maybe. Okay, I think this is not perpendicular, this is parallel. Okay, so here we talk about the Faraday's law. Of course, this is just a simplified version. Later on, we will expand it as a line integral later. But first of all, we will just, sometimes we will just simply use this one. Okay. So here, what is the Faraday's law? So here it says, the magnitude of the EMF E induced in a conducting loop is equal to the rate at which the magnetic flux phi b through the loop change with time. Okay, so in the previous page we already have this phi b, and then it will be changing. It will be changing to generate the current. Okay, so we try to take the derivative. We try to take the derivative of the magnetic flux with respect to time, which means that this is the rate of the magnetic flux changing, or the rate at which the magnetic flux change. Okay, so the keywords are the rate at which the magnetic flux through the loop changes. Okay. So this is, so if the magnetic flux is changing, this derivative will not be zero. Okay. And then we take the negative side and then equals to this EMF. Okay. It will. So this value is related to the EMF. So what is EMF? EMF is actually called electromotive force. EMF. Here it is EMF. This EMF is called electromotive force. Actually, it is not a force. In Chinese, it is called 电动势或者电势能。电动势。Okay. Okay, later on you will know what it is, but it will have a SI unit of volt. It will have a SI unit. SI unit is volt. Okay, like a potential, electric potential. Yeah. But actually, it's not electric potential. It's difficult to explain, but yeah. Just try to accept it is a electromotive force. Will be equal to the negative of the derivative of the magnetic flux with respect to time. Okay, so this is pretty much about the Faraday's law, and then we can use this one. And then for this expression, it is only for a single loop of coil. Single loop of coil. If we have coil of n turns, we just simply multiply it by n on the right side. Okay, so the total motive force will be contributed by all the n turns. So we just multiply this value by n. So this is pretty much it. Okay, so for the title, we mentioned Faraday's law and the Lenz law. Okay, what is Lenz law? We have not mentioned Lenz law yet. Okay, so here it says the minus sign is referred as Lenz law. Okay, so inside this Faraday's law, this is the Lenz law. Okay, so it just tells you, oh, we have a minus sign there rather than a plus sign. Okay, so you may, you feel like, how come there will be a minus sign there? Okay, Lenz find, it should be a negative sign, or maybe he cannot quantify how large it is. But later on, Faraday's law combine the Lenz law and then find that the electromotive force is not only the negative sign, but also with this value d phi b dt. Okay, but I think this law is found in more than 100 years ago. Around 150 or even more, even long time ago, maybe 170 years ago. Maybe I'm not really sure. I have not checked it, but at least I'm really sure it's more than 150 years ago. So at that time, he only need to find there is a negative sign, and then this law is already named after him. Okay, so now it's not possible. But let's see why it is why we worth to mention it as the Lenz law. Okay, so so later maybe we just do this sample problem first. Okay, so here we talk about the Lenz law. So here is a sample problem. So it says the long solenoid S has 220 turns per cm. Okay, so of course we need to change it back to turns per meter as the SI unit. Okay, so and can carry a current I, and then its diameter D is 3.2 centimeter. As its center, we place at 130 turns closely packed coil C of diameter D. And then the current in the solenoid is reduced to 0 at a steady rate in 25 milliseconds. Okay, so it's quite complicated. So let's see what it is. So first of all, it tells you there is long solenoid, which means that the larger one, the blue one is S. The larger one is S, has 220 turns, blah, 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 and then has a current. Okay, so it try to generate, it has a current, so it will generate the B field inside. Okay, if you still remember, the B field generated by the solenoid is a B equals mu 0 IN, if you still remember in chapter 29. Okay, so and then at its center we place another coil C. Okay, so this is the coil C, a smaller one, with only 130 turns. Okay, so this one has only 130 turns of diameter D. Okay, of course the diameter is smaller. This diameter is 2.1. The larger diameter is 3.2. Also, this is 3.2 centimeter. This is 2.1 centimeter. Okay, so the current in the solenoid is reduced to 0. Okay, at the very beginning, the current is I equals 1.5 A. So the current is like at the beginning 1.5 A, and then reduced to 0. Is reduced to 0 at a steady rate in 25 milliseconds. So this is 25 milliseconds, and then reduced to 0 in a steady rate. So this is a straight line. Okay. Yeah. So what is the magnitude of the EMF that is induced in coil C when the current in the solenoid is changing? Okay. So this is not difficult, although the question is quite long. Okay, so of course we are using the Faraday's law, so we need to calculate the magnetic flux and then take the derivative. Okay, so that's the idea. So at the very beginning, the phi B will be B times A. Okay, because in the solenoid we assume that the B field is uniform. The B field is uniform inside, and then B field is 0 outside. Okay, this is the idea in the last chapter. Okay, so so as I mentioned, B is a mu 0 IN. So we have a mu 0 IN for B, and then times A. Okay, so mu 0 is 4 pi times 10 to negative 7. And then I, at the very beginning, is 1.5 A, so 1.5, and then times, this is the number of turn per unit length, but this is centimeter. So for meter, we need to multiply it by 100. So this is 220 times 100 for 1 meter. Okay, so this is mu 0 IN. And then for A, we would need to talk about the cross-section area of the smaller one, because for this cross-section area, the B field is changing, so it will generate the EMF for the coil C. Okay, so we need to mention this is the smaller one, so maybe we can just denote it as AC to mean the cross-section area of coil C. So actually this is pi r square. Pi, we only have the diameter, so this is 0.021 over 2 is the radius. Okay, and then quantity square. Okay, so this is the cross-section area of the coil C. Okay, so this number is 1.44 times 10 to negative 5th power, and then the SI unit is Weber. Okay, so this is for time equals 0, t equals 0, and then it will reduce steadily. Okay, which means that if it is 0, okay, I is 0. So at t equals 25 millisecond, I is 0, so phi b is 0. And then as much as this current is reduced in a steady rate, the phi b also reduced in a steady rate. So which means that d phi b dt, you can just make it like delta phi b over delta t. Okay, so delta phi b is changed from 1.44 times 10 to negative 5 to 0. So 1.44 times 10 to negative 5th. Okay, over 25 millisecond. 25 millisecond. So this number is actually this is negative, because finally this is 0. So it should be 0 minus this 1.44. Okay, so we have a minus sign here. So this is actually negative 5.76 times 10 to negative 4 Weber per second. Okay. Yeah. So so finally we have E equals negative n d phi b dt. So this is the Faraday's law. So we have a negative n. N is this one. This is 130 turn. It doesn't tell you how many turn per unit length. Okay, it only related to the number of turn. This is capital N. That one is small n. Small n is the number of turn per unit length. Okay, so this one is the total number of turn for coil C. Okay, so we have negative 130 times this one is negative 5.76 times 10 to negative 4. Okay, so this number is 75 millivolt. Not large. Okay, but actually we can measure the voltage. Okay, so this is pretty much easy. We only need to calculate the how large the magnetic flux is changing. Okay, and then use the Faraday's law, and then we can find the EMF generated by this the induced EMF. Okay, due to the magnetic flux changing due to this coil S. Okay, so if this coil S generated B field is changing, okay, there will be induced EMF for coil C. Okay, according to the Faraday's law. Okay, so let's have a 10 minutes break.